All right, let's talk math. So let's do a little review here. So what did we say about we defined, it's been a few days, so let's kind of remind ourselves where we start with this. If we want to define the concept of a derivative in terms of limits, what does that look like? So the derivative function for now, we're just going to call it f prime of x. The prime is just there to remind us that it's a function that is born of f of x. It's derived from f of x. We just call it f prime of x. What was that? Okay.
The difference quotient. So f of x plus delta x plus f minus f of x over delta x.
Okay. Because delta x goes to 0. Good. Okay, and remember where that comes from. The picture is really important here. I don't want to waste a ton of time drawing this, but when you study calculus, now and in college, draw lots of pictures. The pictures are important. If you can draw the picture that goes with the limit definition of a derivative, you get it, right? So if here's our function, and that's x, and that's x plus delta x. What is this? Yeah, it's just the slope. The difference quotient just defines the slope of the secant line, and we're taking the limit as we let delta x go to 0, and so that secant line, the 2 points that define the secant line, migrate into 1 point that becomes a tangent line, right? And so, we just end up with something like this. If we draw a slope triangle, that's delta x, and if we call this delta y, really all that is just, f of, that's the point, x plus delta x, f of x plus delta x, that's the point x f of x, which is the difference in the y values. That's it, right? Just the slope of the secant line. That's all we're doing. So we're taking the limit as delta x goes to 0. Now we did come up with one alternate way of writing that, right? Instead of writing it as drawing our picture with an x and an x plus delta x, we could have drawn the very same picture, and I won't go through the whole thing here, but we could have done the exact same process if we called this, and we'll do it the same as the book. We'll call this c, and we'll call this x, right? And then our 2 points become c f of c, and up here we get the point x f of x, right? And the difference quotient this time would just become, the change in x would just be x minus c, and the change in y would just be f of x minus f of c, right? And so we just defined the derivative this time as f prime of c equals the limit of rise f of x minus f of c over run x minus c as x approaches c. That's the way the textbook does it. I think I told you guys I much prefer to make that an x and let c approach x, but it doesn't make any difference. It's the same thing. Same thing. We're not going to use this stuff much longer anyway. I'm going to start showing you the derivative rules pretty soon, and we can just abandon all this limit stuff pretty soon. Okay, so we got these two methods for doing it, and we started to use, we practiced calculating some derivatives using limits. You're great at that. That's the stuff you're still testing on. I mean, we actually did a bunch of the derivatives of the limit quotients before you even knew what you were doing. You already were practicing that stuff. So you're fine with that. Let's talk about some other issues, though. Let's talk today about, we started talking about this, about differentiability. Okay, so where, and this defines where we can, where is the derivative defined? Differentiability is kind of, quote unquote, take the derivative ability. Where do we have the ability to take a derivative? Where is the derivative defined? And there are some places that we're going to uncover here. We kind of started skirting around one of them last week, where derivatives are not defined. Okay? So for one thing, before we do this, I want to draw an analogy. when we talked about limits, right? We talked about limits in terms of two separate one-sided limits, right? We said something along the lines, the limit of f of x as x approaches c equals L if and only if the two one-sided limits existed and agreed, right? So we had to have the limit of f of x as x approaches c from the left equal L, and the limit of f of x as x approaches c from the right equals L. If those are both true, then we said that both the ants are approaching the same point, and we say that the regular two-sided limit exists, right? So we can do something similar to that with derivatives. So we can say something along the lines that our difference quotient, and it doesn't matter which one we pick, we could write either one of these. It doesn't really make any difference. Like if we took the f prime of x and we define it as the limit of f of x plus delta x minus f of x over delta x as delta x goes to 0. That makes sense as a derivative if and only if we can do the derivative, as we approach from the left and we approach from the right and we get the same answers. Okay? So in other words, we would call this the derivative from the left. How do you suppose I'm going to write this derivative if I want to approach from the left?
Same thing as you spelled out, approaches 0 negative.
0, yeah. Agreed? Okay. Right? We'd have to approach 0 from slightly negative values. So in terms of our picture that we drew back here, where was that picture? Right there. So the delta x would actually be negative. That's going to make this point over on the left side of my reference point at x, right? If delta x is slightly negative, and that's okay to do, right? We would just use our secant line on this side instead of on this side of x. And we'll just draw this point in and turn it into a tangent line, okay? So we could do it that way, or if we wanted to, we could write it. What if I wrote it in terms of x's and c's? That's where I could also say f prime of x equals the limit of f of x minus f of c over x minus c as x approaches c from the left, right? And that would just mean that our picture over here, we would have just had x approaching from this side. So x would have been over there instead. Big deal, right? We're still just creating a secant line, okay? And then derivative from the right. It's even worth writing. You know what's coming. Whoops. We'd get f prime of x equals, I'll just call it the difference quotient, the limit of the difference quotient as delta x approaches 0 from the right, or we get the limit of the other difference quotient as x approaches c from the right. Okay? So we could look at the concept of a derivative, and what does this really mean? These ants we talked about earlier in the year, these fancy two-dimensional calculus ants that crawl around on the board, they have this built-in ability to sense their position, but they've evolved to a new stage now where they have little slope sensors too. They can sense their slope. So an ant that's walking towards some point of tangency from the left, right as he's about to take that last step going from left to right, he's gonna simultaneously anticipate what the point he's going to step on. That's what we call the limit. but he's also going to have a sense of what his slope is as he's approaching that point. His slope sensor is going to give him a certain reading, and that's going to be his slope from the left. Alternate ant walking from the right is going to be walking back towards that point of tangency. And what does his slope sensor say on that very last minuscule step towards the point of tangency? That just represents the slope from the right. Okay? So let's use this stuff. What if we want to take a look at calculating a couple interesting derivatives? So let's take the function. How about if we take, and we actually did this one last week, so we'll start with this one. What if we do f of x equals the absolute value of x minus 2? We want to explore the derivative at 2. Okay, so we want to know what's f prime of 2. Okay? So what do we got to do? We got an absolute value function. So what's that tell us? Got to make it piecewise, right? So f of x is going to equal the piecewise function. When is it going to be just the absolute value of hand would just equal hand whenever it's positive, right? So in this case, the absolute value of x minus 2 just equals x minus 2 whenever x minus 2 is greater than 0. Well, if I solve for x, what do I get? X is greater than 2. So on that domain, the absolute value of x minus 2 just has the behavior of plain old x minus 2. It's equal to negative x minus 2 whenever x minus 2 is negative. So when x is less than 2, everybody agree? And then it would equal 0 when x equals 2, right? So if we wanted to calculate the derivative at 2, then this is a piecewise function, so we're going to have to calculate one derivative from the right and one derivative from the left. Agreed? Because there's a junction in the function. Bo didn't even know it. Right at x equals 2. Okay, so what we got to fill in the blanks. What's f prime of x then on our piecewise function? So if we're going to take let's take the derivative from the left, how about? So we're down here. Okay, we can use either one of those definitions of a derivative, doesn't matter. Take your pick. How about if we just use the delta x one, right? So f prime of, and I'm going to do something a little different. Instead of calling this f prime of x, I'm just going to go ahead and call this f prime of 2. F prime of 2, and I'm going to make it f prime of 2 minus. Okay, so we're approaching 2 from the left. That's going to equal the limit of f of x plus delta x, but this time it's actually a 2 plus delta x minus f of 2 over delta x as delta x approaches, if we're going from the left, 0 minus. Okay, what's that look like? The limit of, well, my function to the left is just negative, let's rewrite that. Let's just call that 2 minus x. Make it a little easier to write. Okay? So we got the limit of 2 minus x, and I'm plugging in 2, right? Hang on. I got 2 minus this, right? So 2 minus that. Minus f of 2 is just 2. F of 2 is just 2 minus 2. Everybody see that? Okay. I'm evaluating this thing at 2, so instead of an x, we just got a 2 in there, right? Let's not do that. That's confusing. I'm gonna change that. I don't like that.
Was it 2 minus 2 plus?
Let's not do that. Let's just call it an X. Let's just call it an X for now. In hindsight, we can come back and maybe say, you see how we could have done this, but is this confusing to you, doing the F?
Yes.
Okay,
I'll see.
let's just call it X. Okay, so, did everybody see what I'm doing with this? You'll see why that would have been kind of cool. So f prime of x is just gonna be f of x plus delta x minus f of x. So for our specific function, on this part of the domain, to the left of the junction, remember, f of x is just 2 minus x. Wasn't it? Yeah, 2 minus x. So then what's f of x plus delta x? Let's just start all over up here. So what do we get? F of x is 2 minus x, f of hand is 2 minus hand. Agreed? So we're going to get 2 minus x plus delta x minus f of x is 2 minus x all over delta x as delta x approaches 0 from the left. Okay, so when all the dust settles there, if I distribute the negatives, what do we get on the top? 2 minus x minus delta x.
Minus 2 plus x.
Delta x. As delta x goes to 0 from the left. And what do you notice? There's some horizontal cancellation, right? The 2's cancel, the x's cancel. All I get is negative delta x over delta x. Doesn't even matter the delta x, what it's approaching, right? Our answer is just plain old negative 1, right? That's consistent, though, with what an absolute value function looks like, isn't it? If I graph, let's just do this. If I graph the absolute value of x minus 2, you guys all know what that looks like. Oh, if I do this. There we go. Okay, so absolute value, how do I do that? Absolute value x minus 2, there it is, right? Okay, well look what this looks like right there. Here's our v. As an ant is walking towards 2 from the left, what do you notice? It's going downhill. What's the slope? Okay, is it accidental then that the x's all just went away? The delta x is canceled? No, didn't make any difference. It doesn't matter what delta x was approaching here, as long as it's approaching from the left. The answer I'm getting is negative 1, right? It's the same everywhere. It's constant at negative 1. Okay, if we did the same process from the right, you can already anticipate what's going to happen. F prime of x from the right, so we'll call that was minus, we'll call that plus. The limit of, we can just skip over to here, can't we? All the math's the same. Oh, actually, it's not quite. Never mind, because we got a different function. Limit of f of x plus delta x minus f of x over delta x as delta x approaches 0 from the right. Well, this time, if I'm approaching from the right, the function is x minus 2, right? So f of x plus delta x is going to be x plus delta x minus 2 minus f of x is x minus 2 over delta x. Well, look what's going to happen. When I distribute, does everybody agree I'm going to get an x minus an x? I'm going to get a negative 2 plus a 2. And so I'm just gonna end up with delta x over delta x. What's that equal to? 1. Right? Okay, which is consistent with, oh, where'd it go? Come on. There it is. Which is consistent with the slope on this side, right? So if we go back then and we fill in our answers on the piecewise function for our derivative function, f prime of x, it still is a piecewise function. What's the derivative when x is greater than 2? When it was greater than 2?
1.
1. When x was less than 2? Okay, so then what's happening in the middle? How can you have a derivative at 2 if an ant takes a step to the left and he anticipates the slope is -1, he takes a step to the right and he anticipates the +1? Should there be any preference for one or the other? No. So there's no derivative, right? So it doesn't exist, it's undefined at 2. Okay? So what's that tell us then? There's nothing special about this function. The only thing unique about it was it came to a point, right? So just in general then, what can we say about the derivative of any function at a sharp corner? No derivative, right? We call it a sharp corner or a cusp. Sometimes people call it a cusp. But the derivatives don't exist at sharp corners, okay? So that's one place. If we start a little list here of places where derivatives don't exist, that's item 1 on our list. Yeah, I'll actually make it item 2. Fill in a little more up there. Sharp corners. Okay, what about, I'm not going to do this one mathematically, but what if we did something like, we'll just do this one graphically. What if we take f of x equals greatest integer function? Okay, and we want to explore that let's look at the derivative at 1.5. So let's actually draw the greatest integer function. Oh, I'm going to be so mad if what happened here? Oh man, I'd be just absolutely ticked if I lost this thing I built earlier. Did I?
Oh my gosh, you saved that.
Oh yeah. Oh damn, I lost. Pretty ticked. Oh, man. Okay, shoot. I spent some time on that too. Darn it anyway. All right. So here's our floor function, right, or a greatest integer function. Okay, so if we look at the graph of the derivative at 1.5, what's the derivative? 0, right? Because what is a derivative? It's the slope of the curve, right? So if I look at this point, right here, if I look at that point right there, yeah, it's fine. The derivative is 0, horizontal tangent. What if I try to calculate a derivative at x equals 1, though?
You're going to get different limits for what points there is as you're approaching the point. You're going to end up with the same slope as you approach both sides.
Okay, so if I approach 1, now think what's happening. So we actually need to fill in some dots here, right? We know that the greatest integer function, if we input a 1, we get back a 1, right? If I input a 0.99999, I get 0, right? Because think what it's doing. It's giving you the output. The output is going to be the greatest integer that's less than or equal to the input. So this is the one where it's like we're sliding the bead to the left. If we have knots on all the integers on a string, if it's already at a knot, we can't slide it. But if I can slide it, I'm going to move it over to the next knot to the left. So if I start at 0.99999, it's actually a little bit to the left of that knot, it slides all the way to 0, right? So as we approach 1 from the left, think about the line, the secant line we're going to be creating. So I'm going to be connecting that point and that point. As I move closer and closer, I'm just going to get steeper and steeper and steeper secant lines. As I migrate this point towards x equals 1, remember, I never actually get there. I'm just taking the limit as it gets infinitely close, but it never gets there. And so what slope am I actually approaching? So give me more than undefined. Positive infinity, right? Because we're going to end up with, if we calculate a slope triangle, we're going to rise by 1, but we're going to run by 0 plus. Does that make sense? We don't need to go through the whole math to do this. You can just see this visually. As we approach from the left, f prime of x equals, from the left, it equals positive infinity, right? So on this side. What about from the right? Well, as I slide this point back from the right, those two, that just looks pretty horizontal, doesn't it? If I connect these two with a secant line, the secant line is always just horizontal. Everybody agree? So as these points migrate back to each other, yeah, they become a tangent. They never quite become a tangent. They're always two separate points. They're just approaching one single point. And so that secant line stays the same the whole time, though. So from the right side, f prime of x equals 0. Those don't agree, right? And so clearly that doesn't work. Well, why doesn't this work? Because it's discontinuous. Yeah, because it's discontinuous. So any place where the function is discontinuous, it doesn't make sense. It wouldn't make sense anyway, though. We could even kind of skirt that argument and just say the definition of derivatives depends on limits, right? So any place where a limit doesn't exist, the derivative couldn't exist. Think about the places where the textbooks don't really say this, but I want you to know this, because this makes a lot of sense. Think about the places where limits don't exist. They don't exist where there's a break in the function, right? Like that. They don't exist where there's, what else? Where don't limits exist if we go back to the beginning of the year. Breaks in the function, vertical asymptotes, right? It was infinite behavior. Then there's the other crazy one we talked about with the oscillating behavior. Those are all, we don't make an exhaustive list of places where derivatives don't exist. Those are kind of arcane examples, but at least the oscillating one is. But any place where the limit doesn't exist, obviously the derivative couldn't exist because it's built from limits, right? So one thing we always say then, and this is what's written in the textbook, and this is actually a pretty profound statement. Differentiability, why don't you put this in your notes? Implies continuity. In other words, in order for something to be differentiable, it has to be continuous, right? If it's discontinuous, it can't be differentiable, okay? It can be continuous and not differentiable, though, can't it? We just saw an example of that, right? If we look at, well, not that one. If we look at the, I guess I already got rid of it. If we look at the last example, the absolute value function, it's continuous at 2, isn't it? Right? It's continuous. I never have to pick my pen up to draw it, but it's not differentiable there because it's got a sharp corner. Right? So differentiability implies continuity, but not the converse. Continuity does not imply differentiability. Just because it's continuous doesn't guarantee it's differentiable. That's not. Okay, one other example. Let's look at last example. So there's one other piece of our list we got to add. So what if we take, I could do that one. That's going to work. F of x equals x to the third. And we want to look at this at 0. Okay? Let's calculate the derivative here. And this is not a piecewise function. We don't have to be all fancy and calculate the derivatives from the left and from the right. There's no obvious sharp corner in this one. It's a smooth function. So let's use our alternate definition. So f prime of x equals, if we're going to do this at 0, it's going to be the limit of f of x minus f of 0 over x minus 0 as x approaches 0, right? This one makes it pretty easy if we use the alternate definition of the derivative, the limit form. So what's f of x? What's f of 0? Zero, right? Over x, right? So we don't even need that, minus 0. Actually, okay, right. So what happens here then? As x approaches 0, what do we get? So x to the 1/3 over x is equal to what? How do you do that? Get back to properties of exponents. If I divide like bases, what do? Subtract. So this is x to the 1. So this would give me the limit of x to the 1/3 minus 1, right? So that's going to give me the limit of x to the negative 2/3. Well, that's just 1 over x to the 2/3. As x goes to 0, what's that going to do? As x goes to 0, that's going to be what? 1 over 0. In fact, it's actually going to be 0 plus for sure, isn't it? Because it's being squared, right? So if it's 1 over 0 plus, what is that? Infinity, yeah. Positive infinity. You guys are getting this stuff, right? So it's positive infinity. Let's look at the graph and just verify that that makes sense with the graph. Okay, that makes sense, doesn't it? Look at that graph. What's it doing at the point 0, 0, the tangent? Looks pretty vertical, doesn't it? Right? Okay, so that didn't work though. We didn't get a derivative back. So what's our third category? If we go back to our list, where's our list? There's our list. Derivatives don't exist at sharp corners. Anywhere limits don't exist. So discontinuities. And 3, what would we call that last one?
Must be a function.
Well, it is a function. The f of x to the 1/3 is defined everywhere. What's wrong with that, though? Okay, so in terms of a tangent line, maybe. What's going on with the slope of the tangent line? Yeah. So you get a vertical tangent line, right? So it's an undefined slope. So the last place, let's call it that. So those are the places where derivatives don't exist, right? Sharp corners, vertical tangents, anywhere limits don't exist. We out of here in 2 minutes.
Yes.
Oh, man. It's just not enough time. Not enough time. McMinnville, I used to get 70-minute periods for calculus. It was so awesome. We could actually kind of round things out.
So we're looking at 30 minutes after.
Yeah, what's that?
Before that, we had 4 classes every day.
Yes, I would prefer we had longer or fewer classes, for sure.